So what this is um, first review thing that I'm doing for AP1 for the exams. There's a couple things that are important on an incline. So I'm doing this in terms of variables, and I'm going to talk about it both in terms of kinematics, which are motion equations, as well as energy, because you can solve things many times more than one way. So for right now, we're going to ignore friction. We've got a box of mass m sliding down a hill. Again, hill's at angle theta, and the box is going down d. So in terms of forces, um, we want to think about this by breaking gravitational forces into components. Now, if you were asked to solve or to do a free body diagram for this, you would not break that into components in a free body diagram. But many times when they ask you something like this, they'll say, if you need to modify your diagram, do so here, not in the original diagram. So we know that gravity, which is mg, acts straight down. The normal component of gravity is perpendicular to the hill. The parallel component of gravity is parallel to the hill. So via geometry madness, that's a similar triangle. And if you want me to go ahead and prove that, go talk to your geometry teacher, because trust me, it's a similar triangle. And the angle is between the normal component and gravitational force is the same as the angle of the hill from the horizontal of the Earth. So in this case, then, to find the normal component, that's mg cos theta, the parallel component is mg sine theta. So if we want to find the acceleration of this thing, we go back to Newton's second law, which is the master equation of all physics, F net over m tot. The net force here would be the parallel component. That's the only part that's causing this thing to slide down the hill. Why? Because the normal component is opposed by the normal force of the hill acting up and to the right. Again, we didn't draw that here. If you're doing a free body diagram, that would be something that you would see. So the parallel component of the gravitational force is mg sine theta. The mass of the system is m, so the acceleration would be g sine theta. If we were going to find the final velocity of this, we could use a kinematics equation such as vf squared equals vi squared plus 2ax. I think it's written slightly differently on the formula sheet. There is no initial velocity if we start from rest, although I guess there could be. So the final velocity is equal to squared is equal to 2. The acceleration is g sine theta. We found that out earlier. And the distance was d. So the velocity at the bottom of the hill is radical 2g sine theta d. Now, if there is a coefficient of sliding friction, mu sub k, we would go back to Newton's second law, which was up here, but we think about this not as just being F parallel, but F parallel minus the force of friction. Well, friction is equal to the coefficient times the normal force. The normal force in this case is not just the weight of the object, but it's mg cos theta. So force of friction would equal mu, and I put mu k for kinetic, mu k mg cos theta. So to get the overall acceleration, mg sine theta minus mu k mg cos theta over m. Once again, the mass actually cancels out. The coefficient of friction is an indication of the slipperiness or stickiness between two surfaces, but the particular mass doesn't matter. So in this case, the acceleration is g sine theta minus mu k g cos theta. So now, this is pretty complicated. If we want to find the final speed, we could use the same kinematics equation we had before. But the acceleration is more complicated. So it ends up being square root of radical 2gd in parentheses sine theta minus mu k cos theta. So there's a lot going on there. But the main thing really, I think, is drawing this triangle and recognizing what the parallel component is and what the normal component is. The normal component is especially important when friction is involved, as we just saw. Now, I'm going to do the same problem again, but this time solve with energy. Initially, let's say there's no friction. Since nothing's rolling, we don't have to worry about rotational kinetic energy. So the key thing here is looking and showing this. The energy is conserved. E initial equals E final. And if there's no friction, that's absolutely true. A lot of times that'll get you a point on the AP exam. So we have gravitational potential energy is equal to kinetic energy. mg delta H is equal to 1/2 m delta V squared. But now we're going to substitute the specifics in for this scenario. Well, what's the delta H? What's the height? Well, I redrew this hill again. If this is d, this is theta, again, thanks to the rules of trig, this is opposite side. So I know the hypotenuse is d and I know the angle is theta. Therefore, the opposite side would be d sine theta. So I can say mg d sine theta. In this case, I'm going to have 1/2 m v squared. Once again, the mass cancels out. Lo and behold, I get the exact same answer I had on the previous page. V equals radical 2gd sine theta. Again, going back, that's what I had. So in this particular case, now let's assume there is that coefficient of friction again. Here, mechanical energy is not conserved. So I could say the initial energy minus the work done by friction is equal to the final energy. Or you could say the initial energy is equal to the final energy plus the work done by friction. Either one of those would be consistent, but be careful how you think about that. So I wrote it like this. U grav minus work is equal to kinetic energy. So in general terms, mgh is the initial gravitational potential energy. The work done is force multiplied by distance. I'm subtracting that off because the force of friction is acting uphill even though the direction of motion in the distance traveled is downhill. And then that's going to equal my 1/2 mv squared. Well, mu k is equal force of friction over force normal. Force of friction is equal mu k times force normal. Once again, I've got to go back and get the force normal as mg cosine theta. I did this on the front page. So once again, force of friction is mu k mg cos theta. Plugging it back into my energy equation and work equation, and this is the work energy theorem, I think. So I have the mgh is mg, the h was d sine theta. The force of friction was mu k mg cos theta. The distance was just d that it's sliding downhill. And that will equal 1/2 m v squared at the bottom. So once again, all the m's cancel out. So I'm left with, to get v squared, divide both sides by 1/2, which is the same as multiplying it by 2. So get 2 parentheses gd sine theta minus mu k g cosine theta d was v squared. So I can distribute the g and d out, and I get the exact same answer that I had on the first page. Pretty cool, huh? That it can work both ways. I'm going to shrink this down so you can look at it. So that's page 1, and that's page 2.